Hi, I'm Dr. Leiter from Pace University, and before I got my PhD in computer science, I was in the U.S. Army for 26 years. I'm here to introduce you to quantum computing to hack the world. Most of what we will discuss is quantum computing rather than hacking, but we will be building up to a hands-on exercise of how a quantum computer today can hack a search using Grover's algorithm. But there is much to discuss before we can understand how the exercise works. This is our agenda. There are many new words used in quantum computing, so we will cover those definitions. Then we will discuss cryptography. Then we will discuss wave-particle duality, which is a physics idea that is useful in quantum computing. Then we will discuss superposition, which is a key property of quantum computing, and then entanglement, which is another key property. Then we will get to the hands-on part of logging in to the IBM Experience quantum computer online and use Grover's algorithm to hack the search. Moore's law says that every 18 months, microprocessors double in speed. When they do that, they must become smaller, because smaller equals faster. Babbage's engine, an early computer from 1822, was about 1 meter long. Today's silicon wafers are 10 millionths of a meter long. Quantum computers use subatomic or atomic particles that are very small, only 10 billionths of a meter long. One of the most common subatomic particles used is a photon. I have a photon joke for you. A photon checks into a hotel. The concierge asks, "Shall I call the bellhop to collect your bags?" The photon replies, "That won't be necessary. I'm a photon. I'm traveling light." Quantum computing has several purposes. There's cryptography, breaking secret codes and making new unbreakable codes. Medicine and materials. Quantum computers can understand complex molecules in new ways not possible before. We can create new medicines much faster, safer, and better. We can create completely new kinds of materials, like metals that behave like fabrics. Machine learning. Quantum computers can puzzle out patterns essential to artificial intelligence better than we do now. Searching big data. Quantum computers can search and find the connections in massive amounts of data to make it meaningful and useful. Most quantum information today is hype, not real. That's because it is an emergent science, where some of the most amazing ideas are actually both real and hype. I'll give you an example. Recently, there was a paper published from Moscow that said that the Russians had accomplished time travel using a quantum computer. Within 24 hours, MIT researchers published statements saying, "No, that's not true. The Russians have said hyperbole. They have said hype. It's not true. You can't use quantum computers for time travel." The Russians then replied, "Well, here's our paper. These are the experiments we ran. What do you think?" And we haven't heard a lot from MIT since then. So there's a little bit hype and a little bit real that quantum computers could reverse the direct line of time. Bits and qubits. Bits are used in classical or ordinary computers and are value 0 or 1. Qubits are used in quantum computers and are value 0, 1, any value in between 0 and 1, or both 0 and 1 at the same time. This includes -1. Quantum computers need classical computers. Quantum computers do not have memory and need classical computers to store the results. These golden chandeliers are quantum computers. The left one is the IBM's Q Experience, which we will use today, and the right-hand one is a Google one. These chandeliers are chilled by refrigeration to 15 millikelvin, which is colder than deep space. Tied with it is the coldness of the Cold Atom Lab on the International Space Station. The coldest place in the universe are the refrigeration units of quantum computers in Yorktown Heights and the refrigeration units of Google's quantum computers at 10 millikelvin. The next coldest place in the universe is the Boomerang Nebula at a temperature of 1.1 Kelvin. We chill these quantum bits, these subatomic or atomic particles, to get control over them so we can use them for computing. The gold casing helps prevent interference with other qubits in the universe. Basis states in quantum computing. 0 ket means ground state or off and is shown with an arrow or vector pointing to the North Pole. This is called spin up. It can be shown also with a 2x1 column vector of 1 over 0. The 1 ket means activated or alive and is shown with an arrow or vector pointing to the South Pole. This is called spin down. It can also be shown with a 2x1 column vector of 0 over 1. There are two realities in quantum computing, one before measurement, when everything is possible, and one after measurement, which by observation collapses the waveform into only a 0 or a 1, like a classical computer. Before measurement, a qubit can be visualized using the block sphere. Here we can see the 0 ket at the North Pole and a 1 ket at the South Pole. There is a z vector or arrow going from the center of the block sphere to the North Pole and beyond. There's an x vector that is at a right angle to the z vector and a y vector that is at a right angle to both the z and the x vectors. Then there are 3 Greek letters used to identify angles between the vectors. There is the theta, which is the angle between the vector and the z-axis. There is the phi angle, which is the angle between the vector and the x-axis. There is the psi ket, the point at which the vector intersects the surface of the block sphere. Let's review. Theta is a Greek letter used to describe the angle made with the z-axis. That's the north-south moving vector. Psi is a Greek letter that is used to show the point at which the vector intersects the surface of the block sphere. Psi ket is also used to mean the quantum state or waveform. Phi is a Greek letter used to describe the angle made with the x-axis. When we return to the slide on basis states, we see the ket notation clearly, showing that the 0 ket is a vector pointing up and the 1 ket is a vector pointing down, and both of them, being kets, are column vectors. There are many block spheres used in quantum computing, and all of them are based on the same x, y, and z, and theta, psi, and phi symbols, but the best block sphere is the original one drawn by Felix Bloch, for which he won the Nobel Prize in 1952. Let's talk about cryptography, which has been around since the Spartans and Athenians used it in the 8th century BC. Encryption means to hide, to bury, like in a crypt, and comes from the Greek word kryptos. Decryption means to uncover or return to plain sight. Using quantum computers for encryption and decryption is one of the greatest areas of interest and investment. Now I'd like to discuss wave-particle duality. To illustrate wave-particle duality, I'm using images of deep space taken from the James Webb Telescope. Astronomers pointed the James Webb Telescope towards dark parts of the sky where before now they had not seen anything. It revealed many hundreds of millions of stars and star clusters that we were not aware of before in infrared radiation patterns that again confirmed the Big Bang theory first discovered in 1964 by scientists working at Bell Labs. In our universe, when energy cools and slows down, it first becomes subatomic particles that move in waves, just like they do when they are pure energy. As this energy is coherent, these subatomic particles are naturally entangled. There are strong similarities between the quantum physics of the very large, like astronomy, and the quantum physics of the very small, like subatomic particles used for quantum computers. This is one of the first compact galaxy groups ever discovered in 1877 by Edward Stefan in Marseille Observatory. The galaxies are on track to merge with each other. Radio observations reveal that there is a shock wave of intergalactic gas in the intergalactic space between the galaxies in this group, formed by one galaxy falling into the center of the group at millions of miles per hour. This is the Andromeda Galaxy. This contains 100 million stars and thousands of star clusters. This is the Southern Ring Nebula. It is a dying star within a partner star, already now just dust and gas. The dust and gas could become planets. This is the edge of a nearby young star-forming region in the Carina Nebula. The blue stars or blue galaxies are moving toward us. The red stars or red galaxies are moving away from us. You can see here the motion of energy and the edge of the energy resulting in particles, but all are part of the same waves. This image is of a previously unseen part of our universe. It is again considered proof of the Big Bang Theory, first discovered in 1964 by Bell Labs, when scientists recorded cosmic background radiation noise left over by the Big Bang. Superposition is one of two important properties of quantum physics that we use in making our quantum computers work. Quantum bits, qubits, can be value 1, -1, or any number in between. They can also be both 0 and 1 at the same time. Superposition. Imagine the vector rotating randomly around the z-axis until we measure the quantum state. We can imagine psi-ket to be tracing a sine wave in space. This is just one of many proposed motions within the qubit before measurement. Let's do a dimension exercise of x, y, z, and the higher dimensions. Stand up. Your body is the z-axis. Put your left arm straight out at a right angle to your body. That is your x-axis. Now put your right arm straight ahead of you. That is your y-axis. You are in 3 dimensions there, but there's a 4th dimension, time. You are traveling through time. Now put your 3rd arm out into the 4th dimension of time. Be careful to keep it at right angles to all the previous dimensions. Put your 4th arm into the 5th dimension, again being careful to maintain these right angles. These dimensions all being at right angles to each other is called orthogonality. All kidding aside, when subatomic particles exhibit duality, the only motion which can account for both wave and particle action is a helix. The helix is shown in this picture by the moving blue line. The consequence of this helical motion is a production of 2 fields, one magnetic, shown by the red sine wave, the other is electromotive, which is shown by the green sine wave, orthonormal to both the red sine wave and the blue helix. Just as we did in our little exercise in orthonormal angles, all 3 of these motions, the 2 sine wave motions and the 1 helical motion, are orthonormal at right angles to each other. Phase-changing gates illustrate both superposition and coherence. There are quantum gates that are actually lasers that can be used to shift where waves or vectors move. The phase-changing gates shift the waves and can be used to make them synchronize to each other. A series of quantum gates forms a circuit, and we can make a program out of a quantum circuit. See where sometimes the blue sine wave and the green sine wave are nearly the same, and the red sine wave is different? In Grover's algorithm, where we will build a quantum circuit to crack the secret search to find one queen among 4 face-down cards, the red sine wave will stand out and cause the quantum computer to find the queen for the first time every time. More on that later. We end superposition by observation. Observing the wave collapses it, and so we call that observation measurement, and save the answer. The answer is either 0 or 1. Even though when it was in superposition, it was all these different values, once it is measured, it is flattened out into a form that we can understand and store with our ordinary classical computers. Without measurement, quantum computers are useless. The act of measurement is the step that translates quantum computing to regular classical computing. Classical computers can only read zeros and ones, whereas quantum computers can read every number between -1 and +1, and when they are in superposition, they can be in both states at once, both 0 and 1. Measurement means a decision, and the qubit may be indecisive, in which case it may fall one way one time it is measured, and another way the next time it is measured. Because of this, quantum computers are called probabilistic, meaning there is a probability that they find a specific answer based on how many times you ran the quantum computing program on them. Each time you run the program, it is called a shot. So we run the program at least 1,024 times to make sure of our answer. It is a great time to be a quantum computing scientist. You just get to sit around and take shots all day long. The symbol in pink is the measurement gate symbol that we will use on our quantum computer circuit when we get to the hands-on exercise. Entanglement. When particles formed, which was about 380,000 years after the Big Bang, they were in such proximity as to all be naturally entangled. In a universe that has been expanding for some 14.6 billion years at an ever-accelerating rate, we must now artificially entangle the qubits in our quantum computer in a specific pattern in our quantum circuit. Entanglement is when two or more qubits have exchanged something between them, so that when you take an action on one of them, the others that are entangled with it change in exactly the same way across all space and time instantly. This happens faster than the speed of light, which is an amazing property of quantum physics. Entanglement was first discovered in 1935 by Carl Anderson of Caltech. He was investigating how clouds form, so he made cloud chambers and exposed them to ionizing radiation from a piece of radium. That piece of radium was split in two. One half remained in Arizona, and the other half was sent to Switzerland. A photograph was taken of the clouds in each chamber at the same time, and the clouds were identical. This was as if they had found two identical snowflakes. It was impossible to believe. What had happened was that the two pieces of radium were already entangled, so their effect as ionizing particles on the water droplets forming in the cloud chamber were also entangled. The scientists did not understand what had happened, and were not able to reproduce this experiment or submit it to other scientists for peer review. This is the first ever photograph of two entangled photons, taken in 2019 at the University of Glasgow in Scotland. This is a picture of the setup that those scientists used to confirm they had indeed entangled the photons. The photons were sent from the lower left corner to a beam splitter in the center of the picture, and then one photon went straight to a reader and had its photo taken, and the other photon went left through a bombardment of bouncy castle exercises before finally getting to a reader and having its photo taken. Both were exactly then seen as in the photo, looking like mirrors of each other, because they are still entangled. Whatever happened to one happened to the other in the same way, instantly. Now we've made our way through our agenda and are ready to start working on our hands-on exercise with the IBM's QExperience quantum computer and use it to build a quantum circuit that uses Grover's algorithm to hack a search for instant quadratic speedup over any classical computer on the planet. The block sphere vision is one that we need to return to here to understand what we will be doing to our qubits. I made a quick video to show you how a qubit in a superposition state or a pure basis state of 0 ket or 1 ket can express many different kinds of numbers that we can calculate with when we are in the quantum state, even imaginary numbers. Remember that once we get to measurement, to convert the quantum calculations to the plain zeros and ones that we can use to store our results in our ordinary classical computers, the waveform collapses and we lose that information that it used to calculate with. So let's look at the video now. This is an example of how a qubit can be used to express many different numbers that are between 0 and 1. We have here a description showing theta equals 0. That's the theta angle is this z-axis. That's the angle that it's representing, which is turning around on this point, like these two arrows were showing. And then the phi axis, which is the x-axis. So this is z, and there's an x-axis. So if I move this ball, you can see that theta changes its value from 0 to different values as phi moves, phi is staying at 0, but phi is now twisting on the x-axis, twisting through the center, and then it will move this vector, the red vector, all the way down until it is 180 degrees from the 0 ket. Now it is value 1 ket. These values are, as it twisted around this centerpiece, which is, this centerpiece here, the x-axis. This was what was turning. So when you see here, now this is pi, theta is now valued 3.14, which is pi, and phi equals 0, but a qubit could be anywhere between 0 and 1 on this block sphere. So I'd like to show you that again really quickly. Theta equals 0, phi equals 0. It's pointed towards the 0 ket, the North Pole, and then we move it along the x-axis until we get to the South Pole, and now the value is 1 ket. And it's now 180 degrees different than the 0 ket. Many different values can be included. If we turn this so that we can see more carefully the imaginary numbers, which are on the y-axis, we can see those eyes. Then we can see that many imaginary numbers are possible to be included in our calculations. So many different numbers other than just 0 and 1 can be included in a quantum bit, a qubit. Let's cover some gates that we can use to build quantum circuits. The X gate flips the qubit. It is called the flip gate. It performs a rotation of 180 degrees around the x-axis. Rotation around the x-axis causes the qubit to invert or flip the state vector from 0 ket to 1 ket, or from 1 ket to 0 ket. The Hadamard gate moves the energy off the z-axis and towards the x-axis and is required to make superpositions. Symbol for the Hadamard gate is an H. You can see that the Hadamard gate is a mix of 0 ket and 1 ket, somewhere in between. The controlled NOT gate acts on 2 or more qubits. 1 or more qubits acts as the control, shown as the dark filled-in circle. The other qubit by itself and in a large crosshair is the target qubit. When 1 or more of the control qubits are a value 1 ket, then they fire and hit the target, flipping its value from 1 ket to 0 ket, or from 0 ket to 1 ket. If the control qubits are a value 0 ket, then they do not fire and nothing happens to the target qubit. The H gate plus the C0 gate results in entanglement. The measurement gate collapses the waveform and delivers either a 0 or a 1 for an answer, returning the value of the qubit to either 1 ket or 0 ket. Now we will log into the IBM QExperience quantum computer and use its drag and drop composer to make our quantum circuits. Let's go to https://quantumcomputing.ibm.com. You have to establish a login there. Then we click on the grid symbol on the upper left corner of the screen and select IBM Composer. So this is what it looks like when you've logged into IBM Composer. If you're not looking at this kind of a screen, what you need to do is go up to the grid right here in the upper left-hand corner and click there. And you see that there's a menu of different places that you can go. There's like a dashboard, a challenge, documentation, different programs that are available in a lab. What we're going to look at is IBM Composer because it's the easiest way to visualize quantum computing. So we're going to click there on Composer. And here I have already saved my circuit, which is the Grover's algorithm. Grover's algorithm is a way of search that is quadratically faster on a quantum computer than it is on an ordinary computer. This search for Grover's algorithm is when you already know what you're looking for. In this case we're looking for the queen. The queen is value 1, 1. And she is at position number 3. This computational basis states, these are in binary. And this shows the state vector on their Q sphere. We could also show phase angle, which would show the pi and show the ket notation. The probability of using Grover's algorithm, of finding the queen at state 1, 1, this is using a simulator. In the real quantum computer, there is some error, so it wouldn't be exactly 100%. Okay, so how did I get these gates that build up these circuits here on this composer? We call it a composer because of these wires. The wires remind us of music. And some of the equations used in quantum computing are similar to equations used in music. So the word composer just comes easily to mind. This is quantum qubit number 0. And it is the first qubit with a wire upon which we place the gates. This is quantum qubit number 1. And we put gates here too. Now here are 2 classical registers, classical computers, regular computers. And this is where we're going to store our results. They're either going to be 0s or 1s. This 0 here means that in the first classical register, we'll store the 0 register. We're going to store the measurement that comes from qubit number 0, that wire. And this measurement gate will store the results from the second qubit wire. Here we have our gates. How did they get here? Well, this here came from this palette full of all kinds of gates that I can choose from. If I need to delete a gate, I right click and I cut. So now that cut it, and look, that changed the probabilities because the Hadamard gate had quite a big influence on the result. It now is coming up with a different computation probability of 1024 shots here. I'm going to place my Hadamard gate back. I'm going to grab it, drag it, and drop. And now I return to 1, 1 for the answer. Remember how the X gate, which here looks like a cross tip, how it flips the bits? If I added 2 X gates to the results, I would change the result from 1, 1 to 0, 0. This is in binary, so it would change it from position number 3 to position number 1 because it flipped the bits from 1 to 0 in both cases. I can delete those now. One of them, it now gives me an answer of 1, 0 because the first one will be flipped but the second one will not be. Or I can delete the second one to return the values to 1, 1. So each one of these gates appears in the circuit, in our quantum circuit. You can build quite a few of these. This one is just already built for you by me, but you can have a lot of fun with learning how to build quantum circuits to get the answers that you want. This is where we believe the queen to be, at binary position 1 or decimal position 3. Grover's algorithm is used where we already know what we are searching for, to the exclusion of all other possible answers. In the Grover's algorithm, what is happening is that the quantum computer is trying all possibilities iteratively, but it is so fast that to us, it seems like all possibilities are tried at one instant. Then it finds the answer, which we have told it in advance what to look for. In this case, the answer being 1, 1, which is the same as the queen. To do this, first we place everything into superposition with Hadamard gates. Then we submit it to the oracle, which finds and marks the answer of 1, 1 each time it encounters it. This then is submitted to a part of the circuit called inversion about the mean, which is also called a diffusion operator, where the correct marked answer is amplified. Finally, it is measured, which results in our answer. In conclusion, with Grover's algorithm, we have broken the code in a quadratic speedup, 4 times faster than over conventional classical computing. Grover's algorithm works when we know there is one outcome we want and all the others we don't want. Quantum computers can also use another algorithm, Shor's algorithm, to break all RSA codes, which are the ones used for banking and military cryptography. Shor's algorithm is used when we don't know the outcome we are looking for and must search every possibility. Here's a cartoon. Let's see if you think this is a funny joke. How's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. Can I observe it? That's a tricky question. Thank you very much for the opportunity to share with you quantum computing to hack the world.